usually when you want to operate on, or when you want to work on a system where you have forces and probably some boundary conditions, and you have some internal stresses happening at this object here, in this type of situations, you would always start from a specific coordinate system. x1, x2, and x3. So in this very specific coordinate system, you can project the vector f into the components of f and project the stress sigma into the component of this. And so 2, 2, 3, 3, 1, 3, 2, and 3, 3. Now, you can have multiple stresses at multiple parts of your objects, or you probably have strain as well at the same places. You have the forces as well at the same places. As long as you are working at this under the same coordinate system, you project all the quantities that you are interested in into the same coordinate system, and you operate on them. If you operate or if you work on them, tensors and vectors would be treated just exactly the same like matrices. So all the math that you have learned on matrices and vectors would apply exactly in the same way on these tensors and vectors. So for example, yeah, I think this is the property. So the transpose of a tensor is just you switch all the rows, you make them columns, and all the columns, you make them rows. And the inverse of a tensor is the inverse of a matrix. So the inverse of a tensor is the inverse of a matrix. Multiply the tensor with its inverse, you get the identity matrix, and so on. So for example, if you have a tensor, a random tensor, you multiply it with the transpose of itself from left or from right, you will produce a symmetric tensor. These sort of properties that you have for a matrix, and also for vectors, everything you have learned about vectors calculus would all apply in the same way to the quantities that you have, tensors and vectors. So as long as you are fixing the coordinate system, you don't need to worry about having different components for the stress or for different components for the forces. I mean, just like you did in the past in mechanics, when you work with a force, when you wanted to, for example, to add two forces, you have force F and force, I don't know, probably M. Then in this case, you can work on these two forces exactly the same way as you did in the past. If you want to add them, for example, if you want to multiply them, this is just a vector calculus. Okay, so as I said, what you have learned about matrices, what you have learned about vectors would apply always the same way like you have learned it, as long as you keep the coordinate system fixed. This is one thing I want you to remember. Now, the other thing, the way we write matrices and vectors, I said we have two different ways. We have this way. I'm going to go, this is way number 1. And then we have this way, 1 or 2. This is 1 and this is 2. Now, why would we prefer to write it in this way, not in this one? Because in continuum mechanics, we have some sort of rules. If we apply, we can really write things in a very efficient way. So I'm just going to apply these rules. And I want you to, again, pay attention. This is probably a key idea in the lecture today. I said F as a vector can be written as F1 multiplied by E1 as added to F2 multiplied by E2 added to F3 multiplied by E3. This is something I've just said. Now, how about instead of writing this 3 times, we add a summation? So I running between 1 and 3 for Fi, Ei. This is the same thing, right? Now, how about we agree on some rule here? We say that whenever an index appears twice in the same term, so this is one term, and we have I appearing twice in there. Whenever we have this type of situations, we know that there is a summation over this index between 1 and 3. So in this way, instead of having the summation, as long as we agree on this, we call it the summation rule. So as long as I is repeated twice in the same term, we know that this is going to be added up on the index that is shared between 1 and 3. So F can be written just like F-I-E-I. So this is the summation rule. And then usually for the basis vector, you drop this one. Usually you don't write the basis vector, you just write it as Fi. Okay, so we have jumped from this expression to this one. And both of them are exactly the same. They express exactly the same thing. Similarly for tensors, as I said, a tensor can be written as a summation, but for a tensor you have two indices, 1, 2, 3, 1, 2, 3, and then you have E, I, sigma I, J, E, J, and you add up over these two indices. You can drop this one because you have this is repeated twice, and you can drop this one because you have this one repeated twice, and you can write it in this way. Probably just E1 first, E, I, sigma I, J, E, J. And again, we know that this is just the unit vector, and this is exceptionally done only for the unit vector. I mean, you don't drop anything else. This is just the unit vectors, so this is why we drop them, and then the tensor can be written in this form here. All right, so far we have three ways to write a tensor or a vector. So you can write a vector as in matrix form. Sorry, this is vector F1, F2, and F3. This is equivalent to F1, E1 added to F2, E2, E squared 2, added to F3, E3. And this is equivalent to Fi. For a tensor, I'm just going to write the same thing. You can think about it here. This is sigma 1, 1, 1, 2, 1, 3, and so on. This is equivalent to E1, sigma 1, 1, E1, added to E2, sorry, E1, 2, E1, sigma 1, 2, E2, added to until the rest of them. And this is exactly the same like sigma I and J. Okay, so using this two rules, I mean, first of all, I drop these ones because they are dummies. They don't have any value, and we know that they exist there as long as we have a component with a number. F1 is a component. As long as we know that a component is associated with a direction, this is the direction E1. So the E1 itself is dummy, doesn't add any value. So we can drop that. And this is a dummy index. And we can use the summation rule where things are repeated. Whenever the index is repeated, we can add a summation over that. Now, these two rules are used in continuum mechanics to sum up really very lengthy expressions. And I'm going to show you some examples of that. But before this, let me introduce one last thing. And then we get into the notations and how we apply it. I'll probably just start a new page. I should have started a new page here anyway. All right, see, the identity matrix, you know that the identity matrix can be written in this form. It is 1, 0, 0. I'm talking about 3 dimension here. And the identity matrix, the unique property of the identity matrix is if you multiply any matrix with the identity matrix from left or from right, you get exactly the same matrix. So this is the unique property of the identity matrix. It just replicates things. Now in continuum mechanics, the identity matrix can be written in this form. So delta ij, again, think about this as a tensor, the identity tensor, where delta ij is equal to 1 if I is equal to j, and delta ij is equal to 0 whenever I is different from j. So whenever you have I and j equal, you have this quantity to be 1. When you have them different, it's going to be 0. So in this case, this is delta 1, 1 is equal to 1 because I and j are the same, I and j. Delta 1, 2, 1 and 2 are different, is going to be equal to 0. And delta 1, 3 is equal to a 0 as well. The same is repeated for the rest of them. This is delta 2, 2 is equal to 1. And delta 3, 3 is equal to 1. So this is why we write it in this form in continuum mechanics. And we call this, it has actually a different name, we call it the chronicle delta. Now, I've introduced the chronicle delta, and I've explained about the summation rule. I've explained about the dummy indices. Let us use these three concepts to write really very lengthy and cumbersome expressions in very efficient and summarized way. All right, so I'm just going to show you some examples on that. And by the way, if you look into the lecture notes, or if you look into the presentations, in the presentation, instead of using T with a bar to express a tensor, I'm using bold. I mean, you can use bold to represent a vector or a tensor, or you can just use a bar on top of that, or you can use an arrow on top of that. I mean, different literature would refer to the tensors in different notations. But these specific notations are just to show you that this is specifically a tensor or a vector. And this is some type of a convention. You agree on a convention at the start of a book, and then you follow for the rest of this book, you follow the same convention. For this course, in the notes and in the presentations, I'm using bold because it is easier to use it for printed form. But for my writing, it's not possible to do, just not possible to do the bold. So in my writing, I would be using a bar on top of it. Just a convention. All right. Now, I probably just, I think the example is here. So I'm going to show you examples for the summation rule and basically the dummy indices. So you don't see any indices in here because this is dummy indices. And these expressions here, they basically are written using the summation rule I've just told you about. So the first question is compute or simplify these expressions. So I have delta ij multiplied by delta ij. I want to expand it to the full extent. So you see what is actually this is meant to be. So the full size of it. So I'm just going to do the example here. So you have delta ij, or ij, multiplied by delta ij. Now, you can, I mean, first thing you can see here is that I is repeated. So you have a summation over I, and you have j repeated. So you have a summation over j. So this is written then, since I'm going to expand this, I'm just going to add the summation. I is running between 1 and 3. Another summation for j running between 1 and 3 for delta ij multiplied by delta I and j. So a summation over I, this is just 3 times repetition for I. I'm just going to get rid of this one and write the full length, j between 1 and 3. So I have delta I, so delta 1, j multiplied by delta 1, j added to delta 2, j multiplied by delta 2, j added to delta 3, j multiplied by delta 3, j. Okay, now the whole thing include another summation over j running between 1 and 3. So every j here will need to be repeated 3 times, one for 1, second for 2, and third for 3. So I'm just going to rewrite that as a summation over j. So first of all, I'm just going to replace it with 1. I'm dropping this summation because I'm writing the full sum. Delta 1, 1, added to delta 2, 1, delta 2, 1, added to delta 3, 1, delta 3, 1. And then on the second row, I'm going to repeat j for 2, delta 1, 2, multiplied by delta 1, 2, delta 2, 2, multiplied by delta 2, 2, delta 3, 2, multiplied by delta 3, 2. So this is repeated the second time. And then the third time, I have j to be repeated one more time. This is delta 1, 3, delta 1, 3, added to delta 2, 3, delta 2, 3. See, this is 3 now, added to delta 3, 3, multiplied by delta 3, 3. So this is basically 9 terms all being summed in this expression here. Sorry. So this expression basically is a summation of 9 different terms. Now, we know that if I and j are different, this delta will go to 0. So this is 0, 0. This is 0. This is 0. This is 0. This is 0. And 0. If you look into these ones here you have I and j to be equal. So this will go to 1. This will go to 1. This will go to 1. So if you write them down, here you'll have 1 added to 0, 0, added to 0, added to 1, added to 0, added to 0, added to 0, added to 1, or basically is 1 added to 1, added to 1 is basically 3. This is equal to ij multiplied by ij. So this is the simplification. So it's just a glorified way to write 3. Now I'm probably going to ask you to solve the second example. So the second example is Tij multiplied by delta jk multiplied by delta ki. Just going to write it here. We have Tij multiplied with delta jk multiplied by delta ki. Now it's similar to what we had before in this sense, but instead of having just this one, we have another tensor, which is t multiplied by them. So I want you to try and expand this example. I want you to write it in full length. And if you can simplify something or cancel something, just like we did in the previous example, do it. So I want you to think about it, write it down, try to expand it to the full extent, and then I'm going to show you the solution. So first of all, you look into this expression, you'll see that I is repeated twice. This is I, and this is I. You will also see that j is repeated twice. This is j, and this is j. And you'll see that k is repeated twice. This is k, and this is k. Since I, j, k are repeated twice, you'll have a summation over I and j and k. So this is a summation over I between 1 and 3, another summation for j between 1 and 3, another summation or a third summation for k between 1 and 3. For this expression, Tij multiplied by delta jk multiplied by delta ki. Now, what you need to do is just expand this summation. Expand it first of all for I, and then for j, and then for k. And I'm just going to write the first summation. I'm just going to pick the summation over I and write it in full. So I'm getting rid of this summation because I'm going to write all the terms in detail. So I have the summation over j between 1 and 3, and the summation over k between 1 and 3. They are left in there. And inside, I have I to be replaced with 1, and then 2 added to 2 added to 3. So it is 1j delta j k multiplied by k1 added to t2j multiplied by jk multiplied by k2 added to t3j multiplied by delta jk multiplied by k3. All right, see, I've been able to get rid of the first summation by replacing all i's with numbers. Now I need to repeat the same thing for j. So this term will need to be repeated 3 times. This one will be repeated 3 times, and this one will be repeated 3 times. And then the resulting one, I need to repeat it over k as well 3 times. So in total, 3 by 3 by 3 is 27. I'm just going to show you how to expand it. So I'm just going to take the first term here and repeat it for j, and then take the first of that and repeat it for k. So t1, 1, I'm doing the summation over j. So this is k, and this is 1. Only j is repeated. I need to do the same thing for this one and for this one, but I'm just going to do it for the first one. I'm not going to do it for all of them. So it is t1, 1, delta 1 k multiplied by delta k1 added to t1, 2, delta 2 k multiplied by delta k1 added to t1, 3 multiplied by delta 3 k multiplied by delta k1. Now, this is being expanded into 3, a summation of 3. Obviously, the other ones will expand everyone into a 3. Okay, thank you, Alex. And then I'm going to take this one and expand it another 3 times, because I still have the summation over k between 1 and 3. So this is being expanded again into 3 things. So it is t1, 1, delta 1, 1, delta 1, 1, added to it's t first, t1, 1, multiplied by delta 1, 2, multiplied by delta 2, 1, added to t1, 1, multiplied by delta is 1, 3, delta 3, 1. Now, this will go to 0 because I and j are the indices are different. 2 and 1 are different. 1, 3, and 3, 1 also are different. So this will go to 0. We'll cancel the whole term. This will go to 1, and this will go to 1. So you'll see that this is t1, 1 is the remaining of this expansion. Now you do the same thing, you'll see that the result is going to be t1, 1 added to t2, 2 added to t3, 3. All right. Do you have any questions? If you have any doubts, just I encourage you, please try to expand the full length, and you'll see that this is the final answer. Now, have you noticed any similarities between this example here, the first one we solved, and this one here? If you see, this term here is repeated here. So this one has cancelled quite a few terms and left only 3. So this would do the exact same behavior here. So we have 3 terms left, 1 added to 1 added to 1. In the second case, we have t1, 1 added to t2, 2 added to t3, 3. Now this is happening because if you look into the indices here, the indices will only give a value if I and j are the same. Okay? See, if I and j are the same, you have the same. I mean, you have 1. If I and j are different, you have 0. I'm just going to try and solve the example one more time using this observation. I have delta ij multiplied by delta ij. I know whenever I is equal to j, this will give me 1. Whenever I is different than j, this will give me 0, and everything is going to cancel. So all the terms would cancel. So this is effectively like replacing all the j's with i's or all the i's with j's. So you can write, instead of doing that, you just write delta I and delta I. So instead of writing ij, you basically write I because you know this is going to be exactly the same thing. It's not going to make any difference. Now, you take this one or this one, it doesn't really matter because each one of them is going to make I equal to j, otherwise it's going to be 0. So I'm going to use this one and make I equal to j. And in this case, this one is going to end up being 1 and will leave me with the second part. Okay, so I'll just remove this one here and say that again. See, delta, I mean, pick each one, pick any one you want, and any canonical delta you want. This canonical delta, for example, will be equal to 1 only if I is equal to j. So if I is equal to j, I'm going to take this one and replace I with j or j with I and multiply it with 1, multiplied by 1. So it is basically delta I. This is exactly the same like this one. Now, if you come to this one, you see that this is I repeated twice, so it is a summation over I. You have I running between 1 and 3, delta 1, 1 added to delta 2, 2 added to delta 3, 3. So this is basically equal to 1 added to 1 added to 1 is equal to 3. All right. I want you now to use the same observation and solve the second example. So I have Tij multiplied by delta I k multiplied with delta, or probably with jk. Yeah, it is jk multiplied by delta ki. I will solve it again. You take this guy here. This guy will be equal to 1 if I and k are the same. Otherwise, 0, and it's going to cancel out everything. So I'm just going to take it equal to 1 and replace all the k's with i's. So Tij multiplied with delta ji multiplied by 1. Now the 1 will just disappear. Now again, this guy here is equal to 1 when j is equal to I, otherwise is equal to 0, and it's going to cancel out everything else. So I'm just going to replace every j with an I and get this to be 1. So it is Ti multiplied by 1. Again, I just remove the 1 because it's just dummy to have it there. Now I have Tii. Tii is repeated, so the index I is repeated twice. This is I and this is I is repeated twice. So I have to add a summation over I. So this is a summation over I between 1 to 3 to Tii. This is equal to T11 added to T22 added to T33. So it is a summation over